2, 1, welcome back. This one is on restrictions on domains for rational polynomials. Now, when you're dealing with functions in grade 11, which you're going to find, at least for myself, when I used to take this as a student, I found it actually a little bit confusing on trying to figure out, when do you restrict and when do you not restrict on a particular domain for rational polynomials. If you have a polynomial and there's no and it's not rational, meaning there's no denominators at all, then it's not really a big problem because your domain can be pretty much any input that you have, so any real number. But when you have rational polynomials, so you have a numerator and a denominator, then you do run into problems because you have to restrict the denominators in such a way so that you don't get zeros in the denominator, right? You don't want to have an undefined or an indeterminate number coming up from a particular input. So let's take a look at a few examples here, and I have actually quite a few here because I was thinking of, okay, what are kind of all the different little things that happen and expose you to these so that you can kind of make your own notes and then think about it so that when you are taking this and your teachers are asking you about it, you can kind of restrict the domains properly. All right. Okay, so let's get started. So here's example number 1. I'm going to kind of break them down one by one. And hopefully by the end, once you see all of these, you're going to be a little bit more comfortable with trying to restrict and then create your domain for these rational polynomials. So here is one. We have 2x divided by x plus 1. Now, this right here never gives us any problems, meaning the numerator. What gives us the problem is the denominators. And right here, this denominator, if you take it, so if we have x plus 1, what we do not want happening, we do not want this to be equal to 0. And so if it does equal to 0, then, we get an output, we get a result, which is undefined or indeterminate. Okay, so for functions, we want to have a determinate, kind of result. So we want to know what the answer actually is. We want a number out of it. So what we do is we always restrict these in such a way so that we do not get a 0. Now, when will this equal to 0? Well, this one is very easy to solve. It's going to equal to 0 at x is equal to -1. And what would happen is if you substituted -1 into this function, then what you would get is, you would notice that in the denominator you would get 0, in the numerator you would get this. So this is undefined as a number. And this is not something that we want for functions, right? We want a very unique one number out of this. So our restriction within here is, for this, is we cannot have x is equal to -1. And as a result, if you're creating a domain, now domain is always a set, so we want all our x's, in this case, we'll assume that we are dealing with kind of real numbers, so they are real, however, so such that x cannot be equal to -1. So that's our restriction. This isn't anything new, and maybe you've seen this in some of my other kind of grade 11 videos, so that's kind of the starting point, but something for you to think about. Here is example number 2. So this example is a little bit harder. Okay, so I'm going to take this one out. All right, so let me copy it. And I'm going to bring it down here. So that's my example number 2. Now, technically, when you get these, so when you are dealing with these functions, whatever they are, they're probably going to look like this. They may not always be nicely factored for us, as I have done so right here. Now, I've done this because the factoring component, I have done videos and we've kind of led up to this particular video. Now, if you've forgotten about factoring and you want to be able to see this, I'll put up a link up above in terms of the review if you're interested. Here, okay, let's concentrate on what happens after you factored. Okay, all right, so here we go. So we go from here, we get our factored form right there. Now, once we have our factored form, again, the numerator isn't really a big of an issue for us, but the denominator is. So now we have 2 factors here. We have one factor, which is 4x plus 1, And then we have a second factor, which is just x minus 1. I'm going to drop the brackets here. And what I do not want is, I do not want each factor to be equal to 0 ever. Because again, if it does equal to 0, we're going to get an undefined or an indeterminate result for our answer. And we cannot have that, okay, if we want to keep it as a function. So within here, so now if I do this, I can again kind of rearrange this, and I'm going to get that x is 0 at negative 1 over 4. So that's one of the zeros that we would get run into. And then this one is x is equal to 1. So my restrictions for this denominator will be in 2 points. So x cannot be equal to 1, and it cannot be equal to negative 1 over 4. And if you're creating a domain out of this, then again, so what we would do is we would try to make sure that our domain, so again, it's a set, and our set, okay, so it's all the real numbers. However, x cannot be equal to that, and x cannot be equal to that. Now, sometimes we just put a comma, okay, so I just put both of these inside here. So that's my second example to you. So far, these ones are very understandable, okay? Now, let's take a look at the third example, which isn't really difficult, but it does bring about questions, okay? So I'm going to copy this, and I'm going to bring it down here. I'm going to paste it right there. Let me change the color. Okay, so now when you have rational functions, right, you can simplify them. And I've done a video on it where we're just kind of basically simplifying these rational polynomials. I'll put up a link up above there, okay, for kind of numerous examples on how to do that. But in that video, I didn't really talk about restrictions because I wanted to leave it to this video. So here you have basically, okay, a function. So that, notice that I have a x in the numerator and then I have an x in the denominator. So technically, they will cancel and I'm going to get a very simple, just a flat line, right? And within here, so a lot of students, what happens is when they cancel, they forget that although the x's cancel, you still have to restrict your denominators for the actual function. Because, okay, so notice within here, our denominator, so basically we cannot have x is equal to 0. That's coming from the denominator. And sometimes students will say, but hold on, didn't they cancel? So, you know, what's the problem? Well, remember that, yes, they do cancel, but we do not know exactly where these things are coming from. Math is trying to model something for us. And maybe this is coming from some kind of a system where, you know, you do have these consecutive things and they're multiplying each other. Okay. However, notice that if they are in kind of sequence within and the multiplication happens, it's fine for all the values of x, but you're going to run into a problem if you're going to try to substitute 0, because what you're going to get is you're going to get this. Now, we know that this is undefined, but even so, you know, even if you would got this, then this is indeterminate, and we can't have an indeterminate answer within as a function, because what will it be, right? So that would be the question. So we still say that this is kind of undefined at 0. So although it cancels, don't forget to still set the restriction, okay, on all of the values for your input that make the denominators equal to 0. So here, our domain is nice, you know, it's still everything, but unfortunately we cannot make this equal to 0. And I'm going to just show you, because even if you use a tool like Desmos to try to graph it, you know, I'm going to show you that we're going to get a flat line. So let me do that for you. So there you have it. Okay, so, you know, you might get fooled because you look at this, Desmos plots this whole thing in, and you'd be like, oh, okay, it just is set at 1 there, right? So if I zoom in here, but, okay, if I'm going to go, okay, along here, you'll notice that even Desmos, okay, at 0 gives you an undefined answer, So that's what you have within there, and you can see that. So there is actually no value for the output at that. So be careful when you're setting those. So that was another example. Okay, so let's continue with this trend, because this is where it just continuously gets a little bit more annoying. So I'm going to take another example. So let's say this one. Okay, I'm going to copy it. Now you can have a lot of fun with this one. If you wanted to, you can factor this thing out. So I factored it for you. So what I did was I basically took this. So this was the original rational polynomial, okay? And clearly, as you can see, it's pretty annoying. Now it is a quadratic, so you know it can be factored possibly. And it turns out that it can be factored into this. So I've factored this whole thing out. Now, we're just talking about restrictions. Obviously, things will cancel. You have the 3 and the 3 canceling. That's not a problem. Those are just numbers. They're not zeros. But where we run into the problem where we have this 2x plus 5 in the numerator canceling out the 2x plus 5 in the denominator. These ones, not a big deal because they're just regular numbers that are non-zero. But 2x plus 5 is a problem. And because it is in the denominator, although it will cancel, you still have to set the restriction, which means that we're going to have to see, okay, when does this equal to 0? So of course, I mean, it's not always too hard to try to solve these. So x is going to be at negative 5 over 2. That's what you're going to have there. And therefore, our restriction is going to be set. Okay, we cannot have this thing at that. Now, that's not the only restriction. Okay, that's only the restriction for the factors that canceled. Now, of course, we also still can't forget that we have this, okay, but this one doesn't cancel at all. And for this one, so what we're going to have is this also cannot be equal to 0. So if I manipulate this, I'm going to get x cannot be equal to, okay, so right here, to that. But I bring this about because, again, just like the previous example, often on tests or quizzes or when students are doing this, they're uncertain because they will factor this out on a test. And then what they will get is, so as a result, so if I factor this whole thing out, what I'm going to get is I'm going to get x plus 1 in the numerator, and then I'm going to get just 3x plus 1 in the denominator. Everything else canceled. And students, what they'll do is they'll say, okay, so this restriction is set, so meaning x cannot be equal to negative 1 over 3, but they forget about that. So you have to set restrictions prior to simplifying your rational polynomials. All right, so please remember that. So as a whole, again, you can set now your domain. Now it can be any x, but it cannot be these two values. That's another example that you have. Now, here I'm going to kind of continue on, and here's your last example, and this one is definitely a little bit annoying. So what we have, okay, I'm going to do this one kind of in full for you. So there it is, and you have multiple things happening. Now, in reality, you know, depending on your teachers, you may not see this, but you would. I probably would kind of throw this in for students to really see, okay, do they understand these restrictions or not? All right. So the first thing in terms of steps as an overall, because notice this isn't actually fully out factored. So I'm going to factor it out for you as well. So first you try to see, okay, so let's factor this out. I'm going to leave this as division for now. Now notice within here, x squared minus 1. That's a difference of squares, so that's going to be x minus 1 and x plus 1. So that's what I'm going to have in the numerator there. And then within here, so in the denominator, I have, so I can take out the x. This is going to be 2x plus 3. So now that's factored. Now in the denominator, so I have now x divided by, all right? And now this right here, that's a perfect square, actually, I'm noticing there. So that's going to be, you know, x plus 2. I'm going to leave it as x plus 2. All right, so or you can write x plus 2 squared if you like. All right, so once you do this, Now what you do is you go to every single rational polynomial. So I have one here, okay? I have a denominator there. I have another one here, I have a denominator there. And I have one here, and I have a denominator there as well. So before you start doing anything, these are the restrictions. These cannot be equal to 0 at all, okay? Before you do any kind of simplifications. So what does that tell me? What that tells me is, so from the first one, I will see that x cannot be equal to -2 because it's going to make that 0. All right, that's the first one. Now the second one, well here, I'm going to have x cannot be equal to 0, right? So that's right here. And then x also cannot be equal to, so now that's from the 2x plus 3. So this cannot be equal to 0, which is going to be -3 over 2x. So -3 over 2. So that's now taken care of. And then finally, this also cannot be equal to 0. So x cannot be equal to, and this is going to be -2. Now we've already had -2, I guess right here. However, okay, check it because it may not always be the same thing as before. So those are going to be definitely some restrictions. Now you can start to proceed and see, all right, okay, so now that I have this, how do I finish this off? Because I'm going to have to try to simplify. So let's see if there are any other restrictions that I'm going to run into and are going to be a problem. So I'm going to do this and rewrite it. Okay, so here, I'm going to take this, so that's going to stay. So this is going to be 3x plus 2. Now the division right here, so this is now going to turn this around for me. So that's going to be multiplication. So let me maybe do it in a different color. That's multiplication. And then that's going to be now x, 2x plus 3. So I'm doing the reciprocal right there. And now x minus 1, x plus 1. All right. So that is coming, okay, from the numerator. Now in the denominator, right, because I'm still dividing by this entire thing here, so that's going to be a problem for me. So now division again, it is multiplication, okay, by the reciprocal. So what I have is I'm going to flip those over. I'm going to bring this back. So just square it now. And then divided by here by x. And now I'm going to have to see, okay, do we have any other restrictions before I start simplifying? So obviously this we've already had. So that was right here. So that's not a problem. But this we did not have, but we do have it now. Right? We do have that problem now. So from here we have additional restrictions that are coming. X now cannot be equal to -1 and 1. That's coming from. So this is 1 and this is -1, right? If you would solve. So that also cannot be there. Now the last one, this one, we cannot have it at 0, although we already have that one originally from there. But still check it. All right, and now you can start to reduce. So as you can see, you know, this x plus 2, it's going to cancel one of these. So that's going to be gone. This x is going to cancel this x. So that's going to be gone. And I think that's pretty much it. So that means this will simplify to 3 and 2x plus 3, only 1x plus 2 in the numerator, divided by the x minus 1 and x plus 1. Now notice, if you simplified this entire thing, you would be fooled to think that the only restrictions are these, right? Because those are the only ones remaining in the denominator. But look how many restrictions you actually had, okay, from going through the steps. And this is really, really important and something that I know I kind of missed when I was in high school. I didn't maybe care as much, and I wanted to really make this video for those students who are going to be interested and want to really kind of get a solid foundation on this. So you have a lot of different restrictions within here. Of course, you bring them all together, and then you can create your domain as a final product. So let's say x, so x can be pretty much anything, but x cannot be equal to, now let's go through them. So -1, it cannot be -1. I'll go negative 2, so we forgot that one, negative 2, negative 1, so negative 1, negative 2, negative 3 over 2, that's another one, it cannot be 0, and 1. So notice that's a lot of restrictions that you have within there. All right, and I don't think I missed any other ones there. Okay, I hope this will be helpful for anybody who's going to be trying to learn about these restrictions on rational polynomials. Thanks for watching. Okay, cheers everybody. Bye.